Delighted to be here again today with Mark Jeffery of thelasttheory.com, which is also a YouTube channel called The Last Theory. And if you want a longer interview about Mark's background, you can go to the previous conversation that we had, which tells more about him. But Mark, towards the end of our last conversation, you mentioned that you want to spend the next 10 years on two main things. One of them is a company that you're working on called Open Web Mind, which I believe is a software development product. And the other thing is Wolfram Physics.
Yeah. We talked a little about the Open Web Mind last time at the beginning. Yeah.
So, and maybe towards the end, if we have some time, we can go back and revisit that. But I wanted to ask you, why do you feel like the Wolfram Physics project is important enough to dedicate 10 years of your life to?
Yeah, that's a great question. It's interesting when you think about what you want to work on as you get older. I've heard people say that when you're young, you should try as many things as possible because you don't really know what's going to fit for you, what's going to be the great thing that you want to work on. There might be many things that you want to work on. And then as you get older, because you've got less time ahead of you to invest in learning new things, focusing more on the older things that you've picked up experience on over your lifetime is a good idea. And obviously, Wolfram Physics isn't a new thing, but it's based on a lot of old things that I know a lot about. I studied physics in university. I have been working in computers and computation all of my life, and a little bit of that has been on scientific simulation software. So that very much fits in with what I know. I'm a writer, and so one of my passions is explaining complicated ideas in simple ways, and Wolfram Physics has plenty of complicated ideas in it that I would love to explain in simple ways. So it kind of all came together in terms of my experience. It also came together in terms of it seems to me that this is why I called my website and my YouTube channel and my podcast The Last Theory. This could be the last theory of physics. We've been searching for a theory of everything, well, since the beginning of physics, and we've never quite found it, and maybe we never will find it, but this is the only thing in my lifetime that I've looked at and thought, oh, this could be the last theory of physics. This could be the one that actually gets at the fundamentals that all other higher level theories of physics are built on. And that's just an opportunity that is too good to pass up. So that's why I kind of immediately saw this and thought, oh, okay, I want to know more about this. I want to work on this.
Okay, I'm going to be like a little kid and ask why again. Why do you think this might be the last theory? What is it about the theory that is so compelling?
Yeah, another great question. I think it kind of fits in for me with ideas that I'd had previously about what feels good in physics and what doesn't feel good in physics. So what doesn't feel good in physics is all of the extremely complex mathematics that physicists over the last few decades have been focusing on, and the ever kind of more complicated theories of things like string theory, for example. I never really was excited about that because it just seemed like, one, I would never understand it because the mathematics is just far too complex for somebody like me, and two, something that complicated just doesn't feel right. I guess if you look back through the history of physics, to all of the greatest ideas that have ever revolutionized physics, they've all been extremely simple. They might have been hard to understand. General relativity and special relativity are hard to understand, but they're very simple in terms of, I don't know, the curvature of space-time gives rise to geodesic paths of matter through space-time, which model both gravity and acceleration in our universe. You can say it in a sentence. It's a very simple theory, even though it's very hard to understand. And that's what Wolfram's physics struck me as when I first learned about it, was that first of all, it fit in with kind of ideas of computation that I'd thought about before. But secondly, it's so simple. It's a graph, and the graph represents space and time and matter and everything. And it just seems to be one of those potential leaps forward in physics where you think, okay, what we had before, we were just getting way too complex. We were trying to explain discrepancies in our theory and what we saw in the universe with ever more complex kind of sub-theories. And this kind of wipes all of that away and potentially explains everything in a much simpler way. So it just struck me as, just looking at the history of physics, one of those ideas that might just simplify everything.
Well, when he first started out, he was talking about one rule.
Yeah.
Trying to find one rule. And that struck me as beautifully, elegantly simple.
Yeah.
And doable. I thought it was doable. And then he started talking about all possible rules in all possible ways, which strikes me as very hard to wrap one's head around. I mean, maybe it's still a simple idea, but it seems very, very complex. So I wonder what you think about that leap that he made.
Yeah, I like it. I like that leap. And the reason I like it is, suppose suppose there was one rule that determined what happens in our universe, and suppose it turned out to be rule number 30, just to pick a random number here. Then we would be left with the question, like, okay, why are we in a universe that's run by rule 30? It doesn't seem very satisfying. It's like, does that mean there's other universes? Is there a universe that's run by rule 29? Is there one that's run by rule 31? Why do we live in the one that's rule 30? It's not quite as satisfying as an answer that would say, okay, well, the universe has got to be this way because that's just the way it works. So when Stephen Wolfram started talking about all possible rules and seeing the universe through the lens of particular rules that make sense to us, but potentially we could look at the universe through the lens of other rules that may make less sense to us in the way that we look at the universe. That seems more satisfying if it can be worked out, in that we would then not be left with that question, why rule 30? It's like, well, it's not rule 30, it's all possible rules. It's just that the way we've evolved as animals makes us more susceptible to interpreting the universe in the context of rule 30, but we could have interpreted the universe in the context of any number of other rules. So it comes back to this thing about simplicity. It's more difficult to understand. All possible rules is way more difficult to understand than a simple, oh, it's rule 30. I can understand that. However, it's more satisfying. I guess that word satisfying comes up again and again for me. Is a good theory of physics is satisfying. It's like, oh, okay, I see that. I'm not left with any further questions like why rule 30.
What's interesting, you used the word satisfying, because I know Sabine Hassenfelder gets very upset by physics people that rely on beauty
yes.
as their barometer, because she says for her, that's a very bad barometer for making a good decision. But so let's look at this for a second. To me, it seems like there's a lot of metaphysical implications as well that are kind of beautiful about the all possible rules in all possible ways, because once you get up to the level of human thought, and we're considering like free will and what it means to navigate through life and run into challenges and difficulties and make a decision that may be not the best decision, but in the Wolfram model, you can diverge and then merge again. And so there's always a way to get back to the path, because there are multiple rules operating. So I'm not trapped by my one wrong decision or my choice of a wrong rule at some point, because I can always find my way back to another rule. So, I mean, I jumped up about 8 levels from
That's right.
maybe 8 to the 400 levels from the bottom. And you don't even need to comment on that if you don't want to. But,
Well,
but that's one of the things I like about all possible rules at all possible times.
Yeah, absolutely. I kind of wish that life were like that sometimes, that you could go back to bad decisions you made decades ago and find well, I guess you can sort of find another path. You just have to, you can't reverse the original decision, but you can find another way to get to what you might have wanted to happen.
Yeah. So I had told you at the end of the last conversation that I wanted to talk about time and space.
Yeah.
And in Wolfram's model. So I want to ask you some questions. I've got some index cards here to ask you questions.
Fantastic.
Yes. So the first one is, in Wolfram's model, he has space and time, and I'll let you explain briefly what those are. Briefly, space is the atoms of space. Everything is made up of the atoms of space in Wolfram's model. I guess you could say space is basically the same thing as matter in Wolfram's model.
Yeah, kind of.
Yeah.
Kind of.
And time is the updating of events.
Yeah.
He uses the terminology consuming the causal edges and then replacing them and going to whatever the rule says to do.
Yeah.
So which one is prior?
Between space and time?
Yes. In Wolfram's model.
Yeah. It's fascinating. So the way that I would put it, I would say that the graph is all there is in the universe, and the rules are all there is in terms of how the graph evolves. So
now when you say the graph,
yes,
do you mean the nodes and the edges, or do you mean some superstructure that's underneath the nodes and the edges that they're sitting on?
No, I mean the nodes and the edges. So
well, okay, so the nodes and the edges are the graph, and the node is the space and the edge is time. The edge is the relationship.
Yeah, the edges are relationships.
So there's really 3 things. There's time and space, and then there's relationships between atoms of space.
Well, I'd say that space is the nodes and the edges. So the nodes and the edges build up this graph that looks like kind of a fishing net that is the structure. Well, it's more than one thing. It's the structure of space, but it's also matter. So going back to your question about matter, it's well, before Wolfram, the way that we thought about space and matter is we thought that matter was something that was in space. So, you'd get a particle like a photon and it would be traveling through space. So you had this thing that was 3-dimensional space and you had a photon traveling through it. And so it was a particle of matter in space. The graph changes that, in that the graph is everything. The graph is both the structure of space and it's the matter that's moving through space. So the matter might be like a tangle of the graph of a particular kind, where the tangle propagates through the graph as a whole, and space is the graph as a whole. So the 2 things, I think, in Wolfram's theory are the same thing, or rather the graph underlies both space and matter.
Well, so at the end of the day, then, everything is connected to everything.
Yeah, so if you want to think about the nodes are just the intersections really of the edges, and the edges are connections. So yes, everything is connected to everything.
So you're connected to me, and we're both connected to the computer, and we're connected to all the photons and protons and neutrons and electrons and atoms in the universe, because somewhere along the line the connection is connected, right?
That's right. There's a whole bunch of edges between you and me. I guess that the fascinating question that arises from that is, are there shortcuts between you and me? I mean, obviously there's a shortcut.
Have you seen that video that he did on wormholes?
Oh no, I haven't.
Yes, so that he started exploring that. Is there a way to jump the graph?
Exactly.
I think he called them long connections, that there would be some long connections through the graph, and would there be a way to travel along those or through those? He did a talk for some space gurus or something, and so he started exploring his theory through that. I'll put a link to it in the show notes.
Yeah, so that's like a fascinating question. So those long links, if you imagine three-dimensional space, if you imagine a fishing net, the intersections of the strings of the fishing net, they're basically connected to the next intersection. Everything is local, to use the physics term for it, in that one part of the fishing net is only connected to the part of it just like an inch away from that connection. So the question we're asking here is this a flat fishing net where to get from one end of the fishing net to the other, you have to go along all the strings between all the connections from one end of the fishing net to the other? Or are there long strings that go from one side of the fishing net directly to the other side of the fishing net? And because these edges or the strings of the fishing net in that analogy they don't have length. So length can only be represented in the graph by there are an awful lot of edges between me and you right now, because you're in one part of the world and I'm in another part of the world, and so we're a very large distance apart. There's a very large number of edges that connect us. But if there were long edges, if there were like one edge directly from where I am to where you are, that wouldn't be, the word long is sort of inappropriate there. It's long in terms of our universe, our concept of space, but it's just as short as any other edge in terms of it being a direct connection between one part of the universe and another.
Well, so wouldn't that be kind of the same thing as non-locality?
Exactly.
Yeah, exactly. And that would be instantaneous. Like you and I right now are talking to each other instantaneously, right?
Almost.
we're this far apart, and yet we're talking to each other almost instantaneously. So,
but I mean, there's a very good explanation for that. There's wires between my computer and your computer traveling over a very large distance, and electrons are traveling along those wires, or photons are traveling along the fiber optic cables for the long distance stretches there. And all of those influences are happening at the speed of light. So it looks instantaneous to us, but it's not really. It's happening at the speed of light. And so there's a slight delay between my talking and you responding. That's all kind of explained by local physics. You know, one electron in the wire has an electrical influence over the next electron in the wire, and so on. It's all local. So non-locality, you're right, that's exactly the right term for what we're talking about. Is there a non-local effect where you can instantaneously, not at the speed of light, but instantaneously have an effect between one part of the universe and another?
Well, in his physics model, wouldn't that work if at some point there was an entanglement between those parts, and then it diverged and hasn't remerged yet, but they're still entangled. And so if they're entangled, then there should be an instantaneous connection between them.
That's right. This is what Einstein hated so much, the idea of quantum entanglement and this instantaneous connection between two particles at opposite ends of the universe. Einstein didn't like it because the whole of relativity is predicated on the speed of light being a constant. And if you work it all out, it means that effectively you can't transmit information faster than the speed of light. And this was, this has always been ever since relativity has been a fundamental concept within physics. The idea of quantum entanglement, where you have two particles that are entangled, in other words, for example, if you know that two electrons emitted in opposite directions, one's going to have a spin up state and one a spin down such state, but you don't know which is which. And then they fly apart to the ends of the universe, and then you have a look at one, and you work out it's in a spin up state. What that means is the other one's in a spin down state. And before they reached the ends of the universe, they were in a superposition of these two states, this kind of weird Schrodinger's cat superposition, where you don't know whether the cat is alive or dead. It's in fact not alive or dead. According to the thought experiment, it's in this superposition of the alive and dead states. And similarly, the particles are in a superposition of the spin up and spin down states. So if you measure this one and you effectively make it into a spin up state through the observation, then you're effectively making this one into a spin down state, which kind of looks very much like an instantaneous connection between an electron at one end of the universe and an electron at the other end of the universe. It actually turns out that you're not transmitting information by doing that, which is kind of a weird saving of Einstein's principle of not transmitting information at faster than the speed of light. But all of these things kind of can be potentially mapped by Wolfram's theory by positing these ideas of long edges between one part of the universe and another.
Mm-hmm. Well, so with the edges, when if it looks like this, then you update it so that it looks like that. That's his thing, you know, right? If it looks like this, you update it so it looks like that.
Yeah.
Updating requires removing some edges over here and then putting them over here.
Yeah.
Right?
Yeah.
Maybe you want to state that more elegantly before I go on with my question.
No, that's great. Okay. Rules are all about deleting and creating edges. That's it.
Okay, so is this a way in the Wolfram model? Do you see that as a way of keeping the entire structure aligned to the rules? Is the updating happening because so when the rule starts propagating, you start getting a structure, and if that structure no longer looks like the rule, then that piece gets aligned to go back and look like the rule again.
I guess you do get some rules that do changes the universe.
Well, let's just work with one rule for right now, because it's too hard to think about every possible rule. But
yes, I agree.
so the rule that you showed on one of your episodes where you showed it propagating. Do you have that handy that you could put that up?
Yes, sure.
Yeah. Because with that rule, it consumes some edges and then it replaces those edges with another, going back to the original set of edges.
Yeah. Would you like me to show that?
Yeah. I think I've got you set up. Here. You should be able to share screen.
Okay, that's great.
For anybody who hasn't been to this YouTube channel, it's great.
Thank you. So I've got it here somewhere. This is the rule I think you're talking about. So this is the one where if we step through it here, it's basically matching those two edges. So the one from 1 to 2 and the one from 1 to 3, and then it's going to delete the edge in red, the one from 1 to 2, and then create these 3 new edges from 1, 2, and 3 to a new node. And if we run that, then you extremely quickly, then you start to get this very complex universe.
But each time you're removing the one edge that isn't fitting the pattern, and you're putting that pattern back in there.
Well, it's not that it's not fitting the pattern. If we go back to the beginning here and match those edges, so the pattern that we're matching, the pattern that we're seeing is you got a node, and I'm just calling it node 1, but you could call it anything, and then you've got an edge from that node to another node, and then to a third node. So that's the pattern we're matching. It's possible to imagine a universe where you can't actually match that pattern. So, for example, if we go to this universe, that rule is not going to work on this universe, because for the rule to work, you need to match 2 edges that come from the same node, and this universe only has 1 edge, so that's just not
okay. So let's go back to the original one. So this is what you're trying to match every time that you update the rules.
Yeah.
So that's what I was saying. You're trying to align to the original pattern. Every time the rule is updated, it's aligning to the original pattern.
Yeah, you're
aligning the new space to the original pattern.
Well, you're sort of searching for the whole universe for this pattern. So if you search the whole universe and you don't find this pattern, then that rule is just not going to work. More likely, you're going to search the universe and you're going to find many instances of this pattern. So
let's just say for conversation's sake that the universe started with this rule.
Yeah.
And then it starts to propagate. The way that it propagates is to keep propagating to this pattern. keeps propagating this pattern throughout, right? I mean, that's what you just said. You remove one node and then you have to rebuild that pattern.
Well, it's sort of finding the pattern. It's not trying to make the universe conform.
But the first one, it's doing something. The first one, it's not finding pattern. The very first step, something's happening there. Show us again. You take 1 and 2 and you erase that.
So I've set up this universe perfectly so that it finds the pattern, because I sort of like did a sleight of hand there, and there's a question.
But something has to happen. Something has to happen at the beginning.
Yes.
And this is the beginning of your universe that you're making.
Yeah, that's right. So yes, so then we run through, we've matched that pattern, and we delete one edge and we create 3 edges, and we've got a new universe now.
So now you have 4 edges instead of 1 edge. I mean, you erased 1 edge, so you had 1 edge, and then you added in 3 new edges. Now the next time you're going to remove 1 edge and add in 3 new edges, or what?
Yep, exactly the same again. So let's run through that. So the first thing we need to do is we need to do that matching. We need to find a node that's got 2 edges coming from it to 2 separate other nodes. So there's actually only, if you search this universe, there's actually only 1 instance where that works. So like this node, for example, there's only 1 edge coming from that node, so that's no good. And this node has no edges coming from it. All of the edges go to it, so that's no good. This one is also no good because it's got 1 edge coming from it and 1 edge going to it. But remember, the rule requires a node that's got 2 edges going from it. So there's actually only 1 rule in this. There's only 1 node in this universe that's a good candidate for that first node. It's this one here, because this is the only node in the universe that has 2 edges coming from it. So when I run the rule again, it looks for that pattern and it finds it only in 1 place. It's only here. So if I step there, that is the only place in this universe where I can apply this rule now.
Now, is it arbitrary as to which one of those edges is removed?
Yes.
Is it always 1 to 3 that gets removed?
So it's a great question. It's arbitrary because the labeling of these 2 nodes, 2 and 3 here, is arbitrary. Instead of calling that node node 2 and this node node 3, I could have called this node 3 and called this one node 2. The rule doesn't require, it doesn't tell me what labels I should use for each of the nodes. So yes, it's completely arbitrary which of those 2 edges is chosen to be deleted.
And then you delete the edge, and then you.
Yep.
Do you have that on there? Okay, so you delete that edge.
Yep, that's right. So I just chose. So if you can see the rule at the top here, it's written out like 1 to 2, 1 to 3 goes to 1 3, 1 4, 2 4 3 4. So 1 2, this edge 1 2 doesn't appear on this side of the arrow. So it's 1 2 is the edge that I'm going to delete. But remember, I could have labeled this node down here node 2, in which case we would have been deleting this edge.
Right.
So it could have gone either way, but in fact, I've randomly chosen to delete this edge. So
you delete the edge and then you rebuild that pattern again.
Then create those. So it's not rebuilding the pattern so much as creating a new pattern. And we don't know whether the new pattern is actually going to match the rule. In the case of this rule, we are going to be able to find a match, but it's not deliberately trying to create a pattern that it can then match in the next step. It just so happens that this rule does create a pattern that we can match in the next step. So if we
but what is this the 3 nodes all pointing towards the center? That is the rule, right?
So the 3 nodes pointing towards the center there.
What do you call that thing if not a pattern? You're removing some edges and you're adding new edges according to the rule.
Yes. Yeah. So there's like 2 patterns. There's the pattern that we're matching on the left-hand side here, and there's the pattern that we're creating on the right-hand side here. And they could be completely different, the pattern that we're matching and the pattern that we're creating. But it turns out that when we do create this new pattern, it turns out that the universe then has a pattern that we can match on the left-hand side here.
Right, but my point is that every time that you replace you you find the pattern, this one needs to be changed, and then you go back to this original, whatever you want to call it. If it's not a pattern, the three things that are coming into the middle, that thing, you replace it every time with the same thing.
Yes, that's right.
Okay,
that's
right. That was my point.
Gotcha.
So in some sense, that updating is always updating to the same. It's adding the same element into the universe over and over and over again, according to the rule.
Yes. Yeah, that's right. Yeah, gotcha. Yeah.
Okay, so it's not just that it's not just that the whatever's doing the updating is just thinking, oh boy, things got jumbled up a bit, so we've got to go over here and pluck out that little bit and put something back in there so we can get back to the original look of things, the original statement.
Yeah, no, it's kind of not trying to do anything. This is like evolution, isn't it? It's like, is evolution trying to create kind of higher intelligence animals? It's kind of not. It's just happens that's what emerged from evolution on Earth. We got higher intelligence animals out of it, and it's sort of the same here. That the rule is not trying to do anything. My computer is just applying the rule completely, unintelligently. It's just saying, I don't know, find a pattern in the graph that matches this, and then we'll apply.
Well, I mean, your computer is not exactly a great analogy because you or somebody else put the rule into the computer already. So
yes.
So there was some intelligence behind the whole thing.
That's true.
Yeah. So so let's go back to this thing about space being matter.
Yeah.
I have kind of an idea that that the universe is the joining of meaning and matter. And so in some sense, space is the matter and time is the meaning. In Wolfram's model, this is the way it would work out, because space is what becomes manifest.
Yeah.
Right. And time is non-manifest, but time is producing these transformations that makes space become manifest through relationship.
Yeah.
Right. So I think that that's a very interesting picture, that time is transforming the non-manifest into the manifest through relationship.
Yeah. Yeah, it's I'm kind of sort of relieved the way that Wolfram physics has separated space and time again. For a century, space and time was sort of joined by general relativity into this idea of space-time, and that never made sense to me. It's like it's fairly obvious that time is kind of different from space. For example, time goes in one direction, whereas space, you can go in any direction. You can go backwards and forwards and up and down, whereas time, I just haven't mastered the trick of going back through time yet. It just doesn't work for me. So time is I don't know, always seemed obviously different from space, and yet physics treated it as the same. And it was a conundrum, and physicists thought about it, thought how can we explain this difference between space and time when our equations tell us they're effectively the same thing. Wolfram physics has made them two completely different things. As you described, space is the graph and time is the evolution of the graph. So yeah, I'm very happy that those are now different things in Wolfram physics. So I don't know.
So what you're saying is that time doesn't really work dimensionally in the way that it does in relativity, because when Wolfram starts talking about the way that we as human beings, we see a single thread of time.
Yeah.
But that in his model, there is no single thread of time.
Yeah.
So basically, he's also saying that it isn't as though time goes forward. In his model, time is updating whatever needs to be updated wherever it needs to be updated. And there's no particular order in the sequence of events because it's causally invariant. Regardless of what order things get done, it always ends up the same.
Yes, yes, it can end up the same. It's fascinating. So it's difficult to get your head around because
yes.
Because we have this concept of time being, it goes past in seconds. It's 1 second, 2 seconds, 3 seconds. It's regular. Whereas if you look at the graph, so in the same way that I described edges as not having length as such, you can't say, well, this edge is, 1 micron long. That's not the way edges work. All edges are just connections between points, so the connections between the nodes of the graph. And so it doesn't make any sense to say that one edge is longer than another edge. So it's the same with time. There's all these updates happening all over the graph. And I don't know exactly what order those updates need to happen in. I'm not sure Stephen Wolfram knows either, but he does have far more of a grasp than I do on how it sort of doesn't matter what order these updates happen in.
Yeah, that's what he says.
Yeah, that's right.
Yeah.
When it comes to causal invariance, it sort of doesn't matter. The thing that makes it so difficult to understand is that we're in the graph. We are actually in the graph. We always think of physics as, okay, so we're outside of space and time, and we're looking into space and time. That's not the way it works. When things happen in the graph, they affect us because we are also in the graph. And so when we think about, okay, so how does our brain perceive time? We have to think about it not in terms of, well, let's say that every update is 10 to the 100th of a second, and so we perceive that's not the way that it works. The length of the updates can't be measured in seconds, but all of that kind of builds up to affecting things at a higher and higher and higher level until they affect our brains, at which point we perceive things as happening regularly in time. It's sort of the same as thinking about general relativity. General relativity is right. You can think of the universe in terms of a 4-dimensional space-time continuum on a very large level. So all of the stuff that's happening at the level of the graph, where space and time are extremely different, can be modeled at a much higher level by Einstein's equations, where space and time are just different dimensions of the same space-time continuum. It's just because it's at such a higher level, it's kind of a generalization. It's kind of I don't know, at this very high level, it looks like this. And it's the same way with our brains. At the very high level at which the graph is affecting our perception of the graph, it sort of looks like time is a continuum, and it goes by 1 second, 2 seconds, 3 seconds, and so on.
Well, so what you just said, I don't know exactly why my brain jumped to this, but I've been thinking about this to me is a problem. Maybe it's not a problem to you, is there's the whole and then there's the part. So when the graph is propagating, is the tangles or the little bits that get made up, if it starts with the parts and it's the parts that build up into the whole, then those parts include such things as atoms, and then molecules, and then and then elements. And so then the atom is a tangle in the graph, and then that gets somehow inside of the molecule that's a tangle in the graph, and then that's somehow inside of the elements that make up my cells, and then that's inside of my cells. So you're getting a lot of tangles there, right? Or is it that the graph is it that the graph is propagating things that then have parts, or what's happening there? Because there's a whole lot of different things that are all inside of something else. I mean, everything in the universe is kind of nested.
Yeah.
So to think of that as propagating out of a manifold, or he says it's not a manifold, but whatever that thing is. To think of the
Yes.
universe propagating out of that when everything in the universe is all nested inside everything else is very complicated to think about.
Yes. Yeah. I mean, one way of thinking about it is a completely reductionist way of saying the graph is all there is, and it's on an unimaginably tiny scale, which is another way of saying that we are on an unimaginably large scale. We're so much larger than these edges and nodes of the graph, that it's really, really hard for us to think, okay, so how does something at this level arise from something at that level? It's beyond our brain power. And so what we do is we make generalizations. We say, okay, well, we see certain features of the graph that make sense to us at a higher level. So particles, for example, they may be just tangles of the graph, but they are persistent. They travel through space over time, and they don't kind of just suddenly disappear into nothing. They carry on until they interact with another particle, another tangle of the web, which they happen to meet somewhere in space. And so we create this concept of a particle to explain that extraordinary complexity of the tangle, the knot in the graph that gives rise to that particle. And then when we try and explain the thing at the next level of complexity, we sort of forget about the graph, because it's just way too complicated to explain molecules at the level of the graph, because molecules are enormous. I mean, if a particle is enormous compared to the graph, a molecule is just way, way more enormous. So instead of explaining molecules in terms of the graph, we explain molecules in terms of atoms, which we then explain in terms of particles, which we then explain in terms of the graph. So it's just the fact that our brain can't comprehend the level of complexity that would be required to explain molecules in terms of the graph. We just have these intermediate levels that make us think, oh, okay, I know what a particle is. That's something I can wrap my brain around.
Well, that does help explain some things to me, because I was trying to understand how Wolfram's model could account for oneness or identity.
So say more about that. What do you mean by oneness or identity?
Well, in one of Wolfram's discussions, he actually mentioned identity. He said identity it comes from the root word always the same, something that continues through time, right?
Gotcha. Yeah,
and he has actually talked at some points. He says, like, when I'm moving my arm through space, when I move my arm through the air, yeah, he probably didn't say space because that's not correct anymore, right? When I move my arm, the graph is constantly rewriting my arm. I mean, the rule is constantly rewriting my arm.
Yeah.
So that anything that is persistent through time is constantly being knitted together by the rule. Otherwise, it wouldn't exist.
Yes. Yeah. So that gives rise to questions.
So then there's an issue of identity.
Yeah.
So obviously my arm is part of my body. So let's just say my whole body is moving. Say I'm jumping.
Yeah.
Then the rule is rewriting my body as a unity of things. My body is a unity. It's a oneness. So I don't know if you've listened to Carl Friston ever talk about, he's a neuroscientist, and he talks a lot about the Markov blanket. Well, first of all, he talks about one of the hallmarks of life is the ability to prevent dispersion. So, like if you drop a droplet of dye into a tumbler of water, the dye will just disperse out into the water. Yes. But if you drop in a droplet of oil, that oil will maintain its unity for a length of time. And so one of the ways that they explain this is with the concept of the Markov blanket. Have you run into a Markov blanket?
I haven't, no.
Oh, I wish I had a picture of it. Well, let's just pause the recording right here and go get one. So we're going to take a look at a Markov blanket. And the idea here is that, as you can see, in a Bayesian network, the Markov boundary of node A includes its parents, and then the children are coming. So the children are down here, the parents are up here, and then the other parents of all of its children. So there's other parents coming from outside. So the important thing about the Markov blanket is this boundary around the outside.
Yeah.
Because so what Friston talks about is that that first of all, a system exists on its own over time by effectively resisting dispersion by random fluctuations.
Yeah.
And in a Markov blanket, the states will move towards the center to resist dispersion.
Okay.
So a Markov blanket, according to Friston, and I mean, this is a statistical thing too, it's a mathematical way of speaking about the boundary that separates states into things that are internal to the system and things that are external to the system.
Yeah.
So because he's talking about human cognition, he's using that boundary to explain that we have in our cognition, we have active states and sensory states. And our sensory states have access to the outside, and that's how we sense things.
Yes.
Right? And then our active states impact the outside.
Okay.
But some of those states do not have access to the inside, and other states do have access to the inside. Yeah. And so it's a little bit like thinking about, if you want to really simplify it down, think about a watch. The inside of the watch is a very complex mechanism or complicated mechanism. But for the user on the outside of the watch, all you have to do is know, does this need to be, do I need to turn the knob to give it more energy, or do I just need to change the battery? And then I look at the time, and that's all I need to know. I don't need to know how it's built inside.
Yeah.
But a Markov blanket is a way of looking at the internal states of a system and what differentiates it from that which is outside.
Yeah.
So it's a boundary issue. So in the Wolfram model, he says the system has to be actively reconstructed at each moment in time in order to resist dispersion. There's a constant updating of events as the system moves through time.
Yep.
So what do you think accounts for oneness in the Wolfram model? Because obviously there is oneness. I mean, yes. A molecule is separate from that which is outside the molecule.
Yeah. Yeah, it's there's so much there that's fascinating. I guess start with that idea of oneness. That's kind of something we learn. Like when we're born, we have no idea what's what at all. We don't know what's me and what's not me, what's outside of my body. And we sort of make an arbitrary cutoff in terms of what we're going to consider me and inside of me and what we're going to consider outside of me. And it sort of is, it comes down to what can I directly control? So when a baby is kind of, waving its kind of arms randomly in front of its face and it sees other things moving in front of its face, it kind of suddenly learns at some point that there's some things that are moving just outside of its control. And there's some things that are moving inside its control. And the things that are moving inside its control, its hands that it can wave in front of its face, are part of itself. And so that's me. I call them my hands. They're part of me. But it's sort of an arbitrary distinction. I mean, it obviously makes a lot of sense biologically, but I can control things way beyond my hands. I can control by pressing a button on my computer something that happens in a data center somewhere, many hundreds of miles away. So does that mean that that data center isn't part of me? I can talk to you, I can influence you, and you can influence me. Does that mean that when you say something to me that causes strange responses to happen inside of my brain, that there's therefore a strong separation between you and me? When you think of it like that, there's not such a strong separation, because you can.
Okay, so but that is that something that's unique to life, though? I mean, that's unique to human life.
So I don't think
let's take an apple.
Yes.
Let's take an apple, for example.
Yes.
Can an apple influence anything outside of itself?
Absolutely. Absolutely. If you place an apple next to an orange, then the skin of the orange becomes more orange.
That's true. Yes, that's true. Yeah, I should have used a different example. Bananas
no
and
matter
apples,
what example
bananas
you use,
and apples have such an impact on the air around them. Yeah.
Yeah.
And we have a tree in our backyard that I'm never supposed to prune during a certain time of year, and I can never remember what time of year that is, because when you do cut into it at that time of year, it releases pheromones, and those pheromones affect something. I can't even remember what.
Yeah.
Either affect the growth of the tree or kill something nearby. I can never remember what it is. But anyway, yeah. I know I'm not supposed to, so I don't prune that tree at all, because I can't remember the rules.
That's the safe way.
And one of the things that that Wolfram said that I thought was so fascinating, he was talking about intelligence, and he was talking about he sees intelligence and consciousness as being that consciousness is not the top rung, intelligence is the top rung, and consciousness is actually something less than intelligence.
Oh, okay. I hadn't heard him say that.
Yeah, and he talks about intelligence as being throughout the universe in varying ways, like even a vortex is intelligent, or anything that is accomplishing problem solving is intelligent. And then he said, as humans, we have two, I guess he would call them problems, two limitations that he thought made us less than. One is that we're computationally bounded, and the other is that we have a single thread of time. But I don't see those as being limitations. Well, it is a limitation, but I don't see it as being a negative, because to me, the single thread of time allows for logic, and the computational boundedness allows for creativity.
What does he mean by computational boundedness?
Well, for example, Rule 30, we cannot outcompute Rule 30. So we just have to wait until Rule 30 is finished, if it ever finishes in eternity.
Yes.
We are computationally equivalent to any other computational system in the universe, regardless of how sophisticated it is. We're all computationally equivalent.
Yeah.
Which means that we're bounded, we're limited. We can't jump ahead. We can't jump the gate. We can't run ahead and figure out how it ends.
Yes.
So that's a limitation on us.
Yeah, that's right. That's basically saying that there's no simplification in the same way that we can simplify the graph by saying this tangle, well, it's a photon. That's a simplification of what the tangle is, but it allows us to make sense of it.
Yes.
He's saying that in terms of computational irreducibility, that in general, you can't come up with those simplifications. You can't find a simpler way of predicting how Rule 30 is going to evolve over time. The only way you can work out how Rule 30 is going to evolve over time is by doing the entire computation. No simplification is allowed. So
where the rules of physics and the rules of mathematics that we have seen and adopted are the computationally reducible slices of the universe that come out of the graph, but most of it is computationally irreducible.
Yeah. Yes, I guess we do have those limitations. I don't know.
But then here's where it ties into what you said before, because he went on to say that there isn't a fundamental difference between a rock that's the future of human consciousness and a rock that is just a rock. And I thought that was interesting because when you're talking about how an apple has influence outside of itself,
Yes.
I was reading an article the other day about how mushrooms, well, first of all, Michael Levin is this neuroscience, cognitive scientist that's working on the communication that at the cellular level, the bioelectrical language that cells use to communicate with each other, to tell each other how to build systems within the body, and very fascinating language that they use. So I saw this article where mushrooms actually also have a language, a system language that they use for talking to the mushrooms within their colony. Although it takes a lot, it's a signal kind of a thing.
Yes, absolutely.
But then there's also like what do they call it? The mycellular connections of tree roots underneath. And they're all connected to each other, and they all communicate with each other about where to get resources and nutrients and all of that kind of thing. Yeah, there's a lot more out there than you ever imagined once you start looking at it.
Again, there's so many things in that. I mean, again, it comes back to this question of identity. You know, where does one tree end and another start? Does it make more sense to think of it as a tree or as the entire, copse of trees as a single entity, a single organism? And it's sort of, there's no real answer to that question. It's like, yes, it makes sense to think of it as a single tree, and it makes sense in the same way as it makes sense to think of you and me as individual human beings, but also there's a lot of connections between us. So it makes sense to think of, our entire culture as a single thing. The boundaries that we put around things are arbitrary. And I think that applies at all levels. Like if you go down to the very lowest level, like if you think of a particle in the graph, for example, it's like, where does that particle begin and where does it end? So if you think of that particle as like a tangle in the graph, so think of it as, going back to the fishing net analogy, you've got a knot in the fishing net. Where does the influence of that knot begin and where does it end? Because of course, you've got a knot, and it's kind of, involves a whole bunch of nodes in the fishing net, a whole bunch of the intersections of the fishing net strings. But it also affects things kind of beyond that, because this part of the fishing net is knotted. It sort of affects the way that the fishing net is laid out elsewhere. You can no longer stretch the fishing net flat, for example, because that knot means that it's sort of going to be stretched around that knot. And how far around that knot is it stretched? Well, actually quite a long way around that knot. And where do you say that knot begins and ends? You can't really say. And say you've got a knot here and a knot there. Where does this one begin and this one end? It doesn't make sense to say that they're completely separate knots, because they are all affecting, they're affecting all of the nodes and edges of the graph in between them and beyond them. So you can think of them as like, let's look at this area of the graph that's got this knot in it, and that's one way of looking at it. Or look at this area of the graph that's got these two knots in it, and think of that as, maybe this is a hydrogen atom, for example, or there'd be more knots within the nucleus of the hydrogen atom representing the quarks. But there's different ways you can think of it. There's different boundaries you can draw, and none of them are right or wrong. It's not right or wrong to think of an individual tree or a copse of trees. It's not right or wrong to think of an individual human or an entire culture of humans. It's just different levels at which we're choosing to draw those boundaries.
Yeah, the language that Jordan Peterson always uses is level of analysis.
Yeah.
It always depends on your level of analysis.
Yeah, absolutely.
So if you start using a time frame of 1 billion years, yes, then our life doesn't have any meaning to it, because in 1 billion years we're all going to be gone anyway. That's the wrong level of analysis.
Yeah.
So speaking about time, here's another question. So as the universe propagates, and you have this beautiful graph, in depending on whether you're looking at it as this tangled net or you're looking at it as the causal edges coming down in this kind of rain of beautiful designs. At a certain point, which is now, you take a slice of that.
Yeah.
And wherever the edges are at that point, that slice in time, every one of those points is a atom of space. And that's what space is at this moment in time, is if you take a slice through that.
Yeah, it's difficult to know whether it's possible to talk about a single moment in time. And for us humans, that makes sense because, as Stephen Wolfram said, as you told me there, we have this single thread of time, this concept of time starting and carrying onwards. But I'm not sure it's like that in reality. I mean, this was one of the concepts that Einstein got rid of, was the concept of being able to talk about an event happening here in space and an event happening here in space as happening at the same time. How would you know they're happening at the same time? The only way that you can measure whether they're happening at the same time is to take a clock and then move it from here to here and check the clock in this. But by that time, everything's passed. And even if your clock works at the speed of light, if you can shine signals between these two different events to say, hey, this is happening here right now, and somebody here says, hey, this is happening here right now, the signal can only travel at the speed of light. And so it's very difficult to say that these two events are simultaneous. And
so how do they, then is it just theoretical when they talk about non-locality and the particles being entangled and affecting each other instantaneously? Is that just theoretical, or have they somehow done experiments? And if they did the experiment, then how did they do it? So
the thing with the instantaneous collapse of the wave function, I'm choosing my words carefully here,
yeah.
Is that you can't use it to transmit information. This is the weird thing about it. You look at that and you look at the experiments they've done, which say this is sort of a real thing, that yes, these separated particles do seem to influence each other in this very strange way. So hey, let's build a communication device where you emit these particles and you measure this electron and you measure it to have a spin up, and so that makes this one collapse into a spin down state. But it turns out you can't create that communication device, because you can measure this electron and find that it's in a spin up state, but you can't decide, okay, I'm going to set this electron into a spin up state, and therefore it's going to turn this one into a spin down state, and therefore we've got a device that allows us to communicate at greater than the speed of light. Unfortunately, it just doesn't work that way. So it sort of seems that there is this connection between these two different parts of the universe, but it's not a connection that allows us to communicate instantaneously between those different parts of the universe.
One of the few things that we cannot monetize.
Sadly, no. Yeah, the patent on that device would be worth a lot of money.
Well, so there's a couple of other things that are very important to me in my universe, and I wanted to ask you if you can find them in Wolfram's universe.
Yeah.
One of them is this. I think that there's a very important thing in the way reality lays itself out, and that would be anomaly. Anomaly being something that that just interrupts something that maybe is not supposed to be there, or it could be an accidental happening. It could be falling into chaos. It could be tripping over something. Any obstacle that gets in the way that is not intentional. It seems like with the rule, everything is intentional. So where do you get the unintentional things? Because there's a kind of a beauty in what happens in response to the unintentional things. In fact, if you take evolution from non-life into life and then going forward as one of your parameters, then the only way for the DNA to gain information over time is for the organism to have to adapt to something in the environment that causes it to increase the amount of information that it has. And so adaptation is essential for growth, and adaptation comes as a result of anomaly. So where is the anomaly in Wolfram's universe?
So I guess I come at it from a very different point of view from you. Your statement there was that the application of the rule is intentional or creates intentionality.
Well, okay, just forget the language. It's very hard to do this stuff without getting that kind of language tied up.
I know. I know.
I don't mean that at all. I'm just saying in his universe, it seems that there wouldn't be anything that doesn't fit.
So yeah, I'm trying to think that there's many different ways we can go from here. So first of all, I would say it's all unintentional. There's nothing intentional about the application of the rule. It just gets applied, and the fact that particles arise from that, and the fact that atoms arise from those particles, and that molecules arise from those atoms, and that life arises from those molecules, and that intelligence arises from that life, all of that is unintentional. There's nothing about the rule that you can look at that rule and say, oh yeah, that's going to give rise to consciousness. It doesn't seem that there's any room for intentionality there. It's all unintentional in that beautiful way that you're describing. It's all kind of happenstance that all of these things do arise from the graph.
Well, so then when life arises in the Wolfram universe,
yeah,
with nothing being intentional, where does the increase in information come from? If there's no necessity to adapt to accidents, to anomalies, I mean, in the universe that we live in, we trip over rocks, and
yes.
we fall in holes, and monsters jump out at us, and people die, and all these things happen. But in this universe, which is constantly updating events to go back to the rule,
yes,
then where is that chaos?
Right. Yes. So I guess a reframing of that question is, where does the randomness arise? It's like it all seems very deterministic, this application of the rule to the graph. It's like you have this rule, you apply it, and this is what happens. Where does all of the randomness that we see in our universe, where does that come from? And I think this is a question that certainly applies to Wolfram physics, but also is applied to all physics ever. So you can go back to Newton's physics, where everything is like this billiard ball universe, where one thing hits another thing and it causes this thing. That there's no room for randomness in Newton's universe. In quantum mechanics, there was an introduction of randomness, in that it seems, for example, like when an atom, a radioactive atom, decays, you can predict the half-life of that radioactive atom, but you can't predict exactly when it's going to decay. You can say, okay, well, there's a 50% chance that it's going to decay in this amount of time. But that introduced an element of randomness when we moved from Newton's very deterministic rules to quantum mechanics. Again, this is one of the things that Einstein really did not like. He said, well, God does not play dice. He didn't like that randomness. But I think it solves, it sort of answers your question, that randomness, where does all this kind of crazy stuff, this happenstance, this arbitrary stuff that happens in their world, where does that come from if the rules of physics are completely deterministic? And the quantum mechanical answer to that question is, well, it's not completely deterministic. There's this element of randomness in everything. And I'm not sure in Wolfram's physics how this comes in. So I haven't read far enough in what Wolfram has written about this, but it seems to me that there is a place for randomness in Wolfram's universe. So, for example, when we were running through the basic application of that rule, and you asked the very good question, is like, okay, so of those two edges, which one do you delete? It could be either of them. The rule matches it both ways round. So which one do you delete? And my answer was, well, I picked one at random because the rule could have matched it either way. So which one do you delete? I don't know, you pick a random one. And so there is a space for randomness to enter Wolfram's physics if you apply the rules in that way. Now, Wolfram's talked about how he applies the rules, and there are different ways of applying the rules, and some of them he talks about more deterministically. So he talks about matching all possible matches of that rule across the entire universe at the same time. And then he runs into difficulties where there's actually different ways of matching different parts of the universe that are mutually exclusive. So you still have to pick one or the other. And so he comes up with a deterministic rule to determine which one you should choose. I actually quite like the element of randomness that comes in. I'm not sure that Stephen Wolfram can completely escape randomness in the way that you apply rules to the graph. And I'm not sure it's desirable, because I think there is randomness in our universe. It's very difficult to explain, for example, why our universe isn't completely symmetrical. Like, why are you different from me? Why it's a very weird thing to arise from a completely deterministic universe for there to be two very different people. And randomness explains that. If there is randomness at this very basic level of how you apply the rule to the graph, then everything is explained there. So I like the idea of randomness. I would like to keep the idea of randomness in physics.
Well, I guess I have a preference for what I would call, I guess I would call it flexibility rather than randomness. But I have yet to find a way to illustrate my ideas the beautiful way that you have illustrated Wolfram's ideas. And at some point, I'm going to have to figure out how to do that, because I think that there is a certain beautifully adaptively flexible way that the universe is building beauty. I mean, I see it all around. So whether it's doing that according to a rule and an operator, or not sure exactly how it's happening, but I've got to figure out a way to illustrate it. So that would be one of my plans. And maybe your open web mind would be able to help me with that.
Yes.
Yes. So why don't you take a few minutes here at the end and remind us again exactly what the open web mind is all about and what you're trying to accomplish there.
Yeah, well, let me link the two things, Wolfram physics and the open web mind, because strangely, the open web mind works on a graph as well. This idea of nodes and edges that applies to Wolfram physics also applies to the open web mind, and that's a complete coincidence, because I was working on the open web mind using this graph of knowledge idea long before I'd ever heard of Wolfram physics. But it's one of these
Isn't
things.
That beautiful? That's really cool.
It's like I'm using the same words in my code that about Wolfram physics as I'm using my code about the open web mind. There's nodes and edges, and that happens all the time in our world. There are certain concepts like matrices and tensors. I was listening to a podcast the other day about NVIDIA, the maker of graphics chips that speed up people's playing of games, and it does it by being able to do complex matrix and tensor mathematics extremely quickly and massively in parallel on a computer chip, which allows games to work really fast, because you can render a physical reality on a two-dimensional screen just a lot faster using these matrices and tensors and all of the other fancy mathematics they have in these chips. And it turns out you can also mine Bitcoin using these chips, using the same mathematics. And you can perform scientific simulations. Physicists and biologists are using it to do their science far faster than their old supercomputers could ever do it, using these massively parallel chips that were designed for games. And machine learning also uses the same kind of mathematics. So it's this kind of single idea in mathematics that just applies at all these different levels. And of course, NVIDIA made a huge amount of money from exploiting the fact that the same ideas can be used in all of these different applications. And I think it's the same with nodes and edges. So nodes and edges obviously applies to Wolfram physics, but it also, and you've mentioned this to me as well, that it also applies to molecules. Wolfram has looked into how molecules can be modeled in the same way that the nodes and edges of the graph of Wolfram physics can be investigated. And so it's at the level of physics, it's at the level of chemistry, it's at the level of biology, it's also at the level of the human brain. Like the
Yeah, I was just going
neurons,
to say that the neurons, it's the same
yeah,
thing. Yeah.
they're connections between nodes. They're exactly the same. And the axons and the dendrites that kind of spread out from each of these neurons are like the edges of the graph between the neurons, which are like the nodes of the graph. And a social graph, like if you imagine the social graph that Facebook has, for example, knowing who's connected to who. Again, it's just a completely different level of things. It's human beings who are connected to other human beings through friendship or through following them on Facebook or whatever it might be. This social graph is also a graph of nodes and edges. That's why it's called a social graph. It's a basic mathematical concept, a graph that it applies at all of these different levels. And so the open web mind is it's inspired by the neurological level, but it also, in the human brain works this way, and so the open web mind also works this way, connections between nodes. But it also applies at the social graph level. A social graph is also connections between nodes where the nodes are humans. The open web mind expands that, okay, well, great, Facebook has the social graph of all humans, but I want the graph of all knowledge. How are different ideas, how are different concepts in human knowledge connected to each other? And this same architecture, nodes and edges, just seems obviously the right architecture because it's the way the human brain works, it's the way that social networks work, and you can just expand it from humans to connecting nodes of any ideas, any concepts.
So could you just give me like one example of how that works?
Yeah. So
I mean, what you've given me right now is like a big picture.
I know.
I can't find my way in there to a particular.
Yeah, that's right. So think about the ways that we store human knowledge and use human knowledge right now. So I mentioned last time, Wikipedia is kind of one way that we store human knowledge on the web. It's got a whole bunch of articles. There's a whole bunch of ideas in them, and we read them in the English language or whatever other language of Wikipedia we're looking at. There's a whole number of connections between those ideas that are sort of semi-coded in Wikipedia, but not in a very usable way. So one way is, for example, there are links between the articles. You can jump from the article on Albert Einstein straight to the article on general relativity. It's a link. The web has always worked that way through links. There's other human knowledge that you can get out of those articles too. So there's basic information, the date of birth of Albert Einstein, for example. There's a list of the fields of physics that Albert Einstein worked on in the Wikipedia article on Albert Einstein. So there's more specific knowledge than simply that these two things are connected. It encompasses the way that it's connected. So that's all great. All that information is there on Wikipedia. It's just not very usable. What I would like to be able to do is be able to manipulate that. It's like, okay, well, here's an article on Albert Einstein. Okay, so give me a list of all the German physicists. That's interesting that there is so much amazing physics going on in Germany in that pre-Second World War period. Who are all the other German scientists that came out of that amazingly productive time in German scientific history? There's not actually a Wikipedia article on that. There's a Wikipedia article on physicists. There's a whole list of physicists, just in kind of alphabetical order. There's not a list of German physicists who were active between 1918 and 1939 in Germany.
Yeah, I'm often looking for that kind of stuff, and it's very hard to do search. Even on Google, it's very hard to do a search for that kind of thing.
Exactly. And the information's all there. The article on Wikipedia about Albert Einstein says that he's German, and so the information's all there. It's just in the wrong format. If you change that format to the open web mind format, where everything is connections between nodes, so there's a connection between Albert Einstein and physics and Germany and the date of birth that he was born, then suddenly you can just generate on the fly the Wikipedia article about German scientists between the wars, and it would just come up with the list of all of the people in that period. So it suddenly becomes a whole more flexible format where instead of just consuming content on the internet by reading the Wikipedia article, you can manipulate the content. You can say, okay, I want to know, or you can just flow through it. You can just kind of get to that point. I was like, oh, this is interesting. All these German physicists, double click on that. I mean, literally double click on that and then change what you're seeing on the screen so that you can navigate through human knowledge and navigate to all of the other German scientists who are active at that time.
In some ways, Wolfram is a little bit like the open web mind because he has so many of these things going on. He does a weekly Q&A for young people.
Yeah.
And he does a weekly history of math and physics.
Yeah.
Where he talks, people ask him questions and then he'll open up some aspect, some period of time of math and physics. And then he has his blog where he writes all these articles. But when he writes an article, it's 200 pages long. And so he did one that was just fascinating on Combinators, on the anniversary of Combinators. And he wrote this whole thing about Moses Schonfinkel, who was the original guy who came up with the idea of combinators way, way, way back when all those German physicists were working. And Moses Schonfinkel's life ties into all these German physicists. And so it lays all of that out in this article. I'll put a link to that. I'll put a link to that in here because it's a fascinating story. And his mind is just like that. And he just dumps it out and writes like reams and reams and reams every day.
His books are 1,200 pages long. It's
well, and I'm sure he cut out thousands of pages before he got down to that point.
I sort of think this is what you're doing as well. I mean, you have so many interests and you see connections between kind of, different aspects of science, for example, that just never really connect normally. And you see those connections and so you're pulling together things that would never have a Wikipedia article about, the connection between, molecular biology and Wolfram physics, for example. But you're kind of putting that together because it doesn't exist. And that's what a human mind is good at. It's like, oh, notice this over here connects with this over here. And that's what I would like the open web mind to be good at as well, is those kind of connections that you're not going to get a Wikipedia article about, but allow you to just to explore knowledge in a much freer and more productive way.
So how do you program that kind of pattern recognition into a machine?
I don't want to. This is one of the crucial aspects of the open web mind. I don't think we need to. I mean, this is what machine learning is right now. It's programming pattern matching into a machine. That's literally.
So you're going to use us as your hive mind.
we are really, really good at this kind of thing. I mean, basic pattern matching. Okay, the computers are pretty good at that, but in terms of diverse connections, it doesn't matter that the machines are so good at that pattern matching, because what good is it if there's some artificial intelligence algorithm on the computer can decide the outcome of something if we as humans don't understand how it did that or how it got there. The amazing stuff happens when we do that work ourselves using the computers to do all of the stuff that we're not very good at, like remembering all sorts of things and storing connections between things that are just way too many connections for our brains to hold, using computers to do that for us, but doing the thinking ourselves. I don't want to do artificial intelligence. I don't want the open web mind to be an artificial intelligence. I want it to be a human intelligence. I want us to be driving it.
Well, we need something like that helps us to drive towards a goal of flourishing and not a goal of tearing each other apart, because we have far too many of those kinds of social networks that are driving polarization rather than driving flourishing and connection. So
yeah. And it's the artificial intelligences that are sort of driving it. It's sort of not us that's doing that driving. It's the artificial intelligences that decide what we get to see in our feeds that's, to an extent, causing some of that division.
Yeah. So you're gonna find a way around that.
Yeah, I'm not interested in that. I don't want the social media. I don't want the computer feeds you something. I want the human explores, not the human gets given a feed, but the human explores what the human wants to explore.
So what's your timeline on that? When do you expect to have something available for beta testing?
Well, when I said 10 years, I said that advisedly, so I don't give myself too tight a deadline here. It's a huge project. I'm slowly putting out visualizations that are based on the open web mind on my visualizations website, Things Made Thinkable. So you can see those at thingsmadethinkable.com. And on my Tangled Web podcast, which you can find at tangledweb.media, I'm talking about what I'm doing with the open web mind. So anything new that I come up with, I'll put out there. It's a general tech and web podcast. So I talk about other things as well, but it all ties back to the open web mind. So I talk about the kind of things that we were just talking about, why I don't think Facebook is the way to go. So it's not directly related to the open web mind, but it all feeds into what I'm trying to do, what I'm trying to change about the way that we use the web.
Well, that's tremendously exciting. And I appreciate with your very busy and very constructive life that you took time out to talk to me.
Oh, this is such good fun. I really enjoy talking to you, and you have such an amazingly broad range of interests, and it's just wonderful to kind of pull some of those out there ideas in. It's like, oh, I hadn't thought of that. That's interesting. So I really enjoy talking to you.
One big question at the end: where did the rules come from?
Yes. Well, if Stephen Wolfram is right and every possible rule is applied, then I don't know, that it's just all rules. It's not like you needed somebody to select rule 30. It's just
you don't need anybody to select the rule, but somebody had to come up with the rules. Somebody had to design the rules. The rules came from somewhere.
Yeah, maybe. You ask all the unanswerable questions.
Yes.
Kind of
think you don't have to answer it then. I just put it out there for the
absolutely.
Universe. Thank you so much, Jeff. Mark. Thank you so much, Mark.
I have two
your last name and your first name at the same time.
Exactly. Yeah. Thanks
Again,
a lot,
Mark Jeffery of thelasttheory.com, of thingsmadethinkable.com, of tangledweb.media, and I will put all that in the description below.
Thanks a lot. I really appreciate it.
Have a great week. Bye-bye.
You too. Cheers. Bye.